So imagine you're reading this bleeding-edge AI paper. It's about a model that literally learns to predict how the physical world changes just by looking at images. Now, normally, these massive models live on these incredibly power-hungry servers in highly specialized labs. But what if you wanted to run it right on your desk? Well, that is exactly the journey we're going to take in today's explainer. We are adopting a complex AI research paper for everyday consumer hardware.
Which really brings us to the big, central question driving this whole experiment. Can a Mac Mini actually replace an AI lab? We are taking complex research, code that was built entirely around high-end Linux systems and dedicated NVIDIA graphics cards, and we're trying to force it to run on the Apple silicon sitting right in front of us. We really want to find out what it takes to yank a research result out of the lab and bring it into the real world.
Okay, here's our roadmap for this explainer. First, we'll cover AI on a Mac Mini, then we'll dive into what LeWorldModel actually is, check out the TwoRoom challenge, discuss adapting the code for Apple Silicon, look at the final results, and finally, wrap up with why this matters.
Let's jump into Section 1, AI on a Mac Mini. Just to give you a quick sense of the consumer hardware we're working with here, it's a completely standard Mac Mini. It's rocking a 10-core M4 chip, a 10-core integrated Apple GPU, and 16 gigabytes of unified memory. So yeah, we are completely bypassing traditional lab hardware for this.
All right, Section 2, what is LeWorldModel? The absolute hero of our little experiment here is built on something called a Joint-Embedding predictive architecture.
To really wrap your head around that architecture, think of it this way. Instead of just crunching raw pixels, the AI learns by comparing abstract representations of a scene. A world model is an AI that learns an internal representation of how an environment actually changes. It doesn't just passively look at a picture and classify objects like older AI models do. Instead, it evaluates possible futures internally. The AI is literally imagining what happens next. So, rather than bumping into walls in reality to figure out what works, it just bumps into walls in its imagination to plan the best actions towards its goal.
Now, standard models, they often attempt to perfectly reconstruct every single future pixel. So if you move a chair in a room, the AI tries to draw exactly what that new room looks like. And as you can imagine, that requires incredibly dense, heavy math. But LeWorldModel operates totally differently. It predicts a compact representation of the future state. This perfectly highlights how planning becomes possible in a smaller, much more useful space. Because, let's be honest, you don't need to perfectly render the future in Ultra HD to know if an action was a good idea. Moving on to Section 3, the TwoRoom challenge. This is how we're testing the AI. So how do we actually know if this AI is working? While the research paper uses a specific benchmark environment known as TwoRoom, it's basically where an agent has to navigate through rooms, avoid walls, pass through doors, and reach a specific target. The evaluation is this rigorous 6-step methodology. Step 1. The system takes in its initial state. Step 2, it identifies the future goal. Step 3, the model evaluates possible plans in its imagination. Step 4, a planner searches through the candidate action sequences. Step 5, it executes the best actions in the environment. And finally, Step 6, it measures whether the agent actually reached the goal. The absolutely crucial point here is that real success means the agent physically gets to the target. It is not enough that the model just loaded into memory without crashing. It actually has to solve the maze.
Section 4. Adapting for Apple Silicon. We're replacing CUDA with Metal.
Okay, this is where our narrative hits its primary obstacle. Research code is notoriously stubborn, right? It just assumes you are running a Linux environment with a massive dedicated NVIDIA CUDA graphics card. But the Apple M4 chip simply doesn't have CUDA. It uses Metal. So, first things first, we had to add a software fallback from CUDA to Apple's Metal Performance Shaders, or MPS, and the CPU. We updated the planner configurations, bypassed some hard-coded Linux-oriented rendering settings, and ironed out some API differences. But here is the most absolutely fascinating engineering hurdle. Apple's Metal and MPS do not support float64 tensors, and those are heavily used in scientific research. So we had to systematically go in and convert those massive floating point tensors down to float32 before moving them to the processor. It's such a cool problem to solve, and it's exactly the kind of invisible, practical friction you face when you leave the pristine environment of the lab. And because we made all those low-level changes, we couldn't just hit run and hope for the best. We had to use a logical, staged testing approach. So the first phase was just a simple smoke test, checking to ensure the checkpoint loaded and basic prediction actually worked. Second phase, running a single TwoRoom case just to verify that the model, the dataset, the environment, and the planner were all synced up and talking to each other. third phase, we ran a small sample of 5 cases, which amazingly reached a 100% success rate. And finally, once we knew the system was stable, we hit the fourth phase, executing the full 50-case paper-like evaluation. Which brings us to Section 5, the final results. Did it actually work?
We have officially arrived at the climax of our reproducibility quest. After all the code adaptations, the tensor conversions, and the stage testing, did our consumer Mac Mini M4 actually hold its own against the lab's published metrics? Let's talk about runtime first. The total local evaluation took 13.85 minutes. Now, I want to be super clear and carefully caveat this. We are not running a race against a dedicated research GPU here. This is definitely not an apples-to-apples comparison. The hardware is different, the backends are different, the execution paths are different. The goal wasn't to prove the M4 is faster. The goal was to test whether local adaptation was even viable and functional.
And here is the triumphant payoff. The original published research paper reported an 87% success rate in the TwoRoom environment. Our adapted code running locally on a little Mac Mini M4 achieved an 86% success rate. The M4 successfully solved 43 out of 50 cases. It came within exactly 1 percentage point of the published research accuracy. That is absolutely remarkable. It proves beyond a shadow of a doubt that the math holds up perfectly even after all our hardware adaptations.
However, to maintain our journalistic integrity, we've got to be very clear about the limitations of this experiment. For one, we only tested the TwoRoom environment, not every single environment discussed in the original paper. Crucially, we used a pre-trained checkpoint. The model was not trained from scratch locally. We merely ran the evaluation locally. Also, the code requires manual MPS availability checks depending on your shell session. And again, just to reiterate, the runtime shouldn't be used to claim consumer chips or outperforming specialized lab hardware.
Section 6. Why this matters. The real impact of the test.
Let's zoom out for a second to understand the broader impact of this local test for the entire community of tech enthusiasts and AI developers. This whole experiment highlights the core divide we often see in modern technology. On one side, you have the lab environment. It requires dedicated NVIDIA GPUs and incredibly exact fragile software dependencies to function. But on the other side, you have the local machine. It demands code adaptation, stage testing, and careful dependency handling on platforms like Apple Silicon. The core takeaway here? It takes careful, deliberate work to move research out of the lab, but modern consumer hardware is remarkably capable of reproducing complex, cutting-edge AI behavior once you build those software bridges. You don't need $1 million lab to participate in understanding the future of AI.
Which brings us to our final provocative thought for the day. If a standard Mac Mini M4 can run a complex joint-embedding predictive architecture LeWorldModel and achieve 86% accuracy, what other research is just waiting to be run right on your desk? The barrier to entry is lowering every single day, and the tools are quite literally right in front of us. I highly encourage you to go out and try reproducing modern AI models on your own machines. Thank you so much for joining me on this explainer, and keep exploring.